So essentially, in today's video, what we're going to be doing is we're going to be using our knowledge of single-sided limits in order to determine the total limit of various piecewise functions. And so a prime example of this is what we have right over here. We're given some function f of x, and it's defined in pieces. We have this particular quadratic expression over here for x is less than or equal to 1. And then we have this cubic function for x is greater than 1. And we're asked to find the limit as x approaches 1 of f of x. And so, this a value over here, 1, is actually the kind of, I guess you could say, like the boundary point between the two pieces of our function. And so what we can do is we can go ahead and think about the single-sided limits over here. So let's actually take the limit as x approaches 1 from values less than 1 of f of x. Let's consider that first. And so from values that are less than 1, we have to kind of look at our two boundaries here. We see that we have values that are less than or equal to 1, and we're using this quadratic expression. And so what we can do is we can use direct substitution for that. So we'll essentially get 1 squared plus 2 times 1 plus 3, which is just going to be equal to 6, right? And then, so we've determined the single-sided limit from values that are less than 1. Let's try now from values that are greater than 1. And so that's going to be right over here. And essentially, we have this boundary over here, x is greater than 1, and we're given this cubic expression over here. So what we can do is we can just use direct substitution, and we'll get 2 times essentially 1 to the third plus 4, which is just going to be 2 plus 4, which is equal to 6. And so we see that we have these two single-sided limits. They both exist, and they're both equal to 6. And so this tells us right over here that the limit as x approaches 1 of f of x is just going to be equal to 6. So let me actually write. Yeah. Alright, let's go ahead and try another one out. And actually, let me just arbitrarily change colors for no particular reason. And so essentially, we're given this piecewise function defined in 3 pieces. This one's a little bit more intense. We have kind of a trigonometric function, a quadratic function, and then a logarithmic function down here. Defined in 3 different pieces, and we're asked to find the limit as x approaches 0 of f of x. And so what we should first do, before we even consider, the single-sided limits, we actually have to look at which functions we're going to be using. So as x approaches 0, if we look at this a value and we look at our different boundaries, we have x is less than 0, and 0 is less than or equal to x is less than 3. And we're given these two particular functions over here, so we don't really have to consider this kind of third region over here where x is greater than or equal to 3, and we're kind of dealing with a logarithmic function. Instead, we mainly have to focus on these two, the first, kind of these top two over here. And so essentially, we can look at the single-sided limits again. So as x approaches 0 from values that are less than 0 of f of x, and then essentially just from values that are greater than 0. So these will be the two single-sided limits. If these both exist and they're equal to each other, then we can determine the total limit. So let's see over here. From values that are less than 0, we have this first boundary over here is the values that are less than 0, the x values that are strictly less than 0. We're using the function 2 sine squared of x. So if we use direct substitution, we'll get 2 sine squared of 0, which we know that sine of 0 is equal to 0, so 2 times sine squared of 0 is also going to be equal to 0. And then we can kind of just use the same logic. We have this other kind of region over here. We have values that are greater than or equal to 0 and less than 3, strictly less than 3. And we're using this quadratic expression over here. So we can use direct substitution, 1 minus 4 times essentially 0 squared, which is just going to be equal to 1. And so here we kind of reached a bit of a problem. We have one of the single-sided limits being equal to 0, the other single-sided limit being equal to 1. So these both exist, however, these are not equal to each other. And so we can say that therefore that this limit over here does not exist. The total limit does not exist. And I mean, we kind of saw examples of this graphically when we kind of were just introducing ourselves to limits. And we saw when we have a piecewise function where the single-sided limits don't agree with each other, then the total limit would not exist. And let me actually change colors one more time because, I don't know, for fun. We have this final function over here. This one is a bit more interesting. We have two regions over here. 0 is less than x is less than 2, and x is greater than or equal to 2, and we're given these two logarithmic expressions, and we're asked to find the limit as x approaches 2 of f of x. And so essentially we're defining two pieces over here, and kind of our boundary point is at x equals 2. And so what we can do, again, one more time, we're just going to go through the same practice. We'll take the limit as x approaches 0 from values less than 0, actually from 0, as x approaches 2 from values that are less than 2 of f of x, and then values that are greater than 2 of f of x. And then what we can do is we can just look again at these boundaries. So we have 0 is less than x is less than 2, and so that will, this function over here, log base x of 2, is going to be what we can think of as like the function we're going to consider when we're taking the single-sided limit from values that are less than 2. And so we can just use direct substitution, so we'll get log, we'll replace x with 2, so we'll get log base 2 of 2, which is just going to be equal to 1. And then when it comes to the values that are greater than or equal to 2, or that are greater than 2, the single-sided limit from values that are greater than 2, we can consider this boundary over here from x values that are greater than or equal to 2. And we have this logarithmic function, log base 2 of x. And what we'll notice is that when we use direct substitution, we'll also get log base 2 of 2, which is in fact equal to 1. So this exists, they're both equal to each other, and so we can thus determine that the limit as x approaches 2 of f of x is in fact equal to 1. And so this over here will be equal to 1. And essentially what we saw is that, you know, we can kind of take a piecewise function and take the individual limits, the single-sided limits, and see if they agree with each other. We can determine that algebraically. And we also know kind of which function we should use based on these different boundaries over here, right? So if we're looking at, like, for example, limit as x approaches 2, we saw which of these two functions we should use depending on the boundary conditions that they gave us right over here. And so essentially when we're thinking about piecewise functions and their limits, then we have to just really be careful and look at the different, I guess you could say, range of x values at which, which correspond to each of these individual parts.